cos of pi minus x divided by e to the power of cos of pi minus x plus e to the power of minus of cos of pi minus x from 0 to pi. Now we know that cos of pi minus x is equal to minus cos x. So I would be equal to integral of e to the power of minus cos x divided by e to the power of minus cos x plus e to the power of cos x from 0 to pi. Let's say that this is equation number 2. So this is 1, this is 2. Adding 1 and 2 we get 2 times I would be equal to integral of dx from 0 to pi, and from this we get I equal to pi by 2. Hence the value of I is equal to pi by 2. Now in the previous lecture we have seen the method of substitution. Now this is one of the most powerful methods of solving indefinite integrals. But now how we are going to use this method for definite integrals? Let's try to understand this. Let I is equal to integral of fx dx from a to b. Now if we substitute x equal to some function of t, that is, let us say that this is g of t, then dx would be equal to differential of g of t into dt. So this is g dash t into dt. Now a would be equal to g of t1 and b would be equal to g of t2. So we write I equal to integral of f of g of t into g dash t into dt from t1 to t2. It is almost the same as that we used in indefinite integrals. We write x equal to some function of t, let us say that it is equal to g of t. Then we write dx equal to g dash t into dt. Now what we do is we try to find out values of t, that is t1 and t2, such that g of t1 equal to a and g of t2 is equal to b. So we write I equal to f of g of t into g dash t into dt from t1 to t2. But before we use this method, there are a few points to remember. But before we apply this method, there are a few points which we need to remember. The first is g of t should be continuous and differentiable in the interval t1 comma t2. So g of t should be continuous and differentiable in this interval t1 comma t2. Second is g of t must take all the values which x take. For example, let us consider this integral. This is dx by 1 minus x square from 2 to 3. While solving for indefinite integrals, we can use x equal to cos t for this substitution. But when we consider this particular case, we see that we cannot use x equal to cos of t, as the maximum value of cos t is equal to 1. So if we put x equal to 2, then 2 cannot be equal to cos t, and 3 also cannot be equal to cos t, because the maximum value which cos t can take is 1. Hence cos of t is not a proper substitution, and hence we should note that g of t must take all the values which x can take. So based on the above method, let's start to solve an IIT problem. Now this problem appeared in 1983, and it says that evaluate sin x plus cos x divided by 9 plus 16 times sin 2x from 0 to pi by 4. So let us say that I is equal to integral of sin x plus cos x divided by 9 plus 16 times sin 2x from 0 to pi by 4. Now what we do is we write 9 plus 16 times sin 2x equal to 9 plus 16 into 2 times sin x into cos x. We expand sin 2x. Now this is equal to 25 minus 16 times sin x minus cos x whole square. We write the value of this as this in this expression to get I equal to integral of sin x plus cos x divided by 25 minus 16 times sin x minus cos x whole square from 0 to pi by 4. Now what we are going to do is we are going to make a substitution. We substitute 4 times sin x minus cos x equal to t. So we differentiate both sides to get 4 times the differential coefficient of sin x is cos x, and the differential coefficient of minus cos x is plus sin x, and hence we get 4 times cos x plus sin x dx equal to dt. Now when x is equal to 0, t would be equal to minus 4, and when x is equal to pi by 4, t would be equal to 0. So I is equal to 1 by 4 into integral of dt by 25 minus t square from minus 4 to 0. Thus I reduces to I equal to 1 by 4 into integral of dt by 25 minus t square from minus 4 to 0. Now we use the standard formula and get I equal to 1 by 4 into 1 by 2 into 1 by 5 into log of modulus of 5 plus t divided by modulus of 5 minus t. We have used the standard formula of 1 by a square minus x square, and the integral is from minus 4 to 0. So we put the value of t equal to 0 and t equal to minus 4 to get I equal to 1 by 40 into log of 1 minus log of 1 by 9, or I is equal to 1 by 40 into log of 9, or I equal to 1 by 20 into log of 3. Thus the value of I is 1 by 20 into log of 3. Thus we see that the method of substitution has made the problem very easy. So let's move on to property number 5. It says that the integral of fx dx from minus a to a is equal to twice of integral of fx dx from 0 to a if f of x is equal to f of minus x, and this integral is equal to 0 if f of x is equal to minus of f of minus x. Now we know that if fx is equal to f of minus x, then it is an even function, and if fx is equal to minus of f of minus x, then it is an odd function. So property number 5 says that the integral of fx dx from minus a to a is equal to twice of integral of fx dx from 0 to a if fx is an even function, and is equal to 0 if fx is an odd function. So let us try to see the proof of this. Now let us take the first case as fx is an even function. Now the property of an even function is the graph of fx is symmetrical about the y-axis. This is the y-axis and this is the x-axis. Now here this is fx, and we clearly see that this is symmetrical about the y-axis. Now integral of fx dx from minus a to a is nothing but this entire portion, that is the area between this curve and the x-axis. Now we clearly see that as this is symmetrical about the y-axis, so this portion, that is, let us say that this is area A, this is equal to this area, let us say that this is equal to A. So we see that this entire area is equal to 2 times A. Now A is nothing but integral of fx dx from 0 to a. This a is equal to integral of fx dx from 0 to a, as this is a point 0. So this entire area would be equal to twice of a, and this is equal to integral of fx dx from 0 to a. Thus we see that integral of fx dx from minus a to a is equal to twice of integral of fx dx from 0 to a. Thus we can clearly see that when fx is an even function, the graph of fx is symmetrical about the y-axis, and so the integral of fx dx from minus a to a is equal to twice of integral of fx dx from 0 to a. Let us take case number 2, and that is fx is an odd function. Now what is the property of an odd function? An odd function is always symmetrical about the origin. So this portion is symmetrical to this portion. Now the integral of minus a to a fx dx is nothing but this area plus this area. Now as we see that the graph of fx is symmetrical about the origin, so this area would be a and this area would also be a, but these are equal in magnitude, not in sign, because this area is positive and this area is negative. Hence we can say that this combined area is equal to this area plus this area. The value of this would be equal to 0. Thus when fx is an odd function, the graph of fx is symmetrical about the origin, and hence the integral of fx dx from minus a to a is equal to 0. Now let us see property number 6. It says that if f of x is a periodic function with period t, then the integral of fx dx from 0 to n times t is equal to n times integral of fx dx from 0 to t. Now what is a periodic function? We have studied it in the chapter on functions that if a function fx is periodic, then f of x plus t is equal to f of x. Here t is the period of fx. So a function repeats itself after a period of t. That is, f of x plus t is equal to f of x. So the property says that if fx is a periodic function with period t, then the integral of fx dx from 0 to n times t is equal to n times integral of fx dx from 0 to t. So let us try to look at the proof of this. Now fx is periodic, so f of x plus t is equal to f of x. The t is the period of fx. Now, if fx is periodic, then it repeats itself after a fixed period of t. So let us say that it starts from 0. So this is the graph of fx, and again it starts repeating after a period of t. So for values greater than x equal to t, so from t to 2t, again it would be of the same nature. From 3t to 2t, again it would be of the same nature, and so on up to n minus 1 into t to n times t. Here n is any number. If we say that this is I, the area is I, then this area would also be equal to I, and this area would also be equal to I, and so on up to this area. Let us say that this area is I, so this area would also be I, this area would also be I, and so on up to this area. Now integral of 0 to n times t fx dx is nothing but the summation of all these areas, and all these areas are equal, so this would be equal to n times I. I is all these areas. Also the value of I is equal to 0 to t fx dx, as the value of this area is integral 0 to t fx dx. So as such we can say that integral of fx dx from 0 to n times t is equal to n into integral of 0 to t fx. Once again, as we know that fx is a periodic function, so it repeats itself after a fixed period. Let us say that this period is t, so this becomes the graph of fx. Now this area would be equal to this area, would be equal to this area, and so on up to this area. Why? Because we can clearly see this from the graph. Now the combined area is equal to n times the individual area, so this is equal to n times I, and I is nothing but integral of fx dx from 0 to t. Thus the integral of fx dx from 0 to n times t is equal to n times integral of fx dx from 0 to t. Let's see property number 7. It says that if fx is a periodic function with period t, then integral of fx dx from a to a plus n times t is equal to integral of fx dx from 0 to n times t. Here n is an element of set of integers. So again, if fx is a periodic function with period t, then integral of fx dx from a to a plus n times t is equal to integral of fx dx from 0 to n times t. Here t is a period of fx and n is an element of set of integers. So once again, let us say that this is a graph of fx, and your fx is a periodic function.